Welcome to this session on research methodology. Today, we are diving into one of the most crucial phases of any research project, data processing and analysis. Imagine spending months collecting survey responses or experimental results, only to be left with a mountain of confusing numbers. How do you make sense of it all? In this video, we will explore the systematic steps required to clean, organize, and evaluate your data so that it tells a compelling and scientifically valid story. Now that we understand what our goal is, let us look at how we handle raw information. Imagine you have just returned from a massive grocery shopping trip. You have bags full of raw vegetables, uncooked rice, and unblended spices scattered all over your kitchen counter. You can't just hand someone a raw potato for dinner. You first need to wash, chop, and organize the ingredients. This is exactly like data processing in research. Then, you cook them together using a specific recipe, which represents data analysis. Without these steps, your raw data means absolutely nothing. Building on that grocery analogy, let us break down the actual data processing phase into 4 critical stages. First, we have editing, where we act as a filter to remove any errors or incomplete responses from our dataset. Next is coding, which involves assigning numbers or symbols to different categories to make them easier to handle. After that, we use classification to group the data based on shared, common characteristics. Finally, tabulation takes all this organized information and arranges it neatly into rows and columns. This systematic preparation is absolutely essential before any mathematical evaluation can begin. Once our data is neatly processed and tabulated, we move on to the next major phase. Data analysis is where the real magic happens. This is the application of statistical and logical techniques to describe, illustrate, and evaluate the information we have gathered. Why does this matter? Because proper analysis allows researchers to uncover hidden patterns that aren't obvious at first glance. It helps calculate the reliability of the results and make future predictions. Ultimately, analysis is what takes a chaotic pile of numbers and transforms it into solid evidence that either proves or disproves your initial research hypothesis. Now that we know why analysis is important, let us look at our first mathematical tool. The arithmetic mean, commonly known as the average, helps us find the central tendency of our data. Conceptually, it gives us a single summary number for a whole group of measurements. In this formula, x bar represents the arithmetic mean. The Greek letter sigma stands for the total sum. The variable x sub I represents each individual data point, and n represents the total number of observations. If the value of n increases while the sum remains the same, the overall mean will decrease. This shows how sample size directly impacts your final average. Before we move on to more complex tools, let us see this formula in action with a concrete example. Suppose you are studying a new teaching method and test a sample of 5 students. Their scores are 70, 75, 80, 85, and 90. We need to find the average score. First, we substitute our 5 data points into the numerator and prepare to add them up. We set n equals 5 in the denominator because there are exactly 5 students. Adding the scores gives a total sum of 400. Dividing 400 by 5 gives us an arithmetic mean of 80. Physically, this means the baseline performance of the student group is 80 marks. So we have successfully calculated the mean. But this brings us to an important question. Is knowing the average enough? The answer is no. While the mean tells us where the center of the data is, it tells us absolutely nothing about how spread out or scattered the data is around that center. If the data is wildly unpredictable, the average alone can be misleading. We need a mathematical measure of reliability to show us if our data points are tightly clustered together or scattered far apart. This is exactly why we use the standard deviation. This need to measure data spread leads us to the standard deviation formula. Conceptually, it calculates the average distance of each data point from the mean. Here, the symbol S represents the sample standard deviation. Inside the square root, we subtract the mean from each data point to see how far off it is. We square this difference so that negative and positive values do not cancel each other out. We then sum these squared differences. The denominator, n-1, represents the degrees of freedom, giving a more accurate estimate for a sample. If data points are tightly clustered, S will be very small. If they are wildly scattered, S will increase significantly. Now that we have our formula, let us apply it to our previous test scores. We already know the mean is 80. First, we subtract this mean from each individual score and square the results. This gives us 100, 25, 0, 25, and 100. Squaring removes any negative signs that would ruin our calculation. Next, we add these together to get a total sum of 250 in the numerator. We divide this by our degrees of freedom, which is 4, resulting in a variance of 62.5. Finally, taking the square root gives us approximately 7.91. Physically, this means most students scored within about 8 points of the average, proving the teaching method produced consistent results. We have seen how to handle numerical test scores. But what happens when your data is made of words? Suppose you conduct a survey and get a messy pile of handwritten answers like, "I like online" or "physical shops." You cannot perform mathematical operations on plain text. Therefore, our first step in processing this qualitative data is a technique called coding. We assign a numerical code to each category. For example, code 1 for online shopping and code 2 for in-store shopping. This crucial step transforms chaotic qualitative text into structured quantitative data that we can actually analyze. Once our text data is coded into numbers, we need a way to understand the distribution of preferences. This brings us to the percentage analysis formula. Conceptually, it tells us what portion of the whole group belongs to a specific category. In this formula, P represents the final percentage. The variable F stands for frequency, which is simply the number of times a specific code appears in our processed data. The symbol N represents the total number of survey responses collected. By dividing the frequency by the total and multiplying by 100, we convert a simple fraction into a highly readable percentage format. If the frequency F increases, the percentage P will naturally increase as well. Let us see how this percentage formula works in a real survey scenario. You have collected a total of 200 survey responses, so N equals 200. After reading and coding all the forms, you find that 120 forms fall under code 1, which represents online shopping. This means our frequency, F, is 120. We substitute these values into our formula, dividing 120 by 200, which gives a decimal value of 0.60. Multiplying this decimal by 100 gives us our final result of 60%. Physically, this tells us that the majority of respondents prefer online shopping, transforming a pile of messy paper into a clear, actionable business insight. To tie everything we have learned together, Let us look at this flowchart of the entire data processing cycle. On the far left, we start with raw data collection, which is our messy, unorganized information. The arrows guide us through the processing filter. First, data editing to clean errors, then coding and classification to organize categories, and data tabulation to structure it into rows and columns. Finally, we reach statistical analysis on the right, where we apply formulas like mean and standard deviation. This entire visual pipeline represents the transformation of chaotic, raw data into meaningful, scientific insights. We have covered a lot of ground today, so let us summarize the most important ideas. First, remember that data processing is the essential filter that cleans, codes, and organizes messy raw data into a structured format. Second, data analysis takes over by using statistical tools to uncover hidden patterns and relationships. We learned that the arithmetic mean finds the center of your data, while the standard deviation is crucial for measuring how spread out and reliable that data is. You now have the foundational tools to turn a collection of meaningless numbers into powerful truth and informed decisions. Great job!